Welcome, everybody. Well, my name is Michiel Rosa. Alex already introduced us, so I'll keep this short. This talk is called Shadows of the Tomb Raider, which means that we're going to talk about shadows and Shadow of the Tomb Raider. And specifically, we're going to talk about how we implemented DXR ray traced shadows in Shadow of the Tomb Raider. Okay, let's look at the agenda. Let's talk a bit about our game. Let's answer the question, why did we choose to do ray traced shadows? Then we're gonna talk about the technology. So we're gonna talk about the DXR shaders. That part will be covered by Holger, and we're gonna talk about the denoiser, and that part will be covered by John. After that, we're gonna talk about the acceleration structure, how we integrate it in our render pipeline, and look at some results and some future work. And at the end, there's room for questions, if we're fast enough. Okay, Shadow of the Tomb Raider. Most of you will probably know Tomb Raider. It's a very well-known franchise. It's been around for a really long time. And Shadow of the Tomb Raider is the last installment of the reboot of Tomb Raiders. So in 2013, there was a reboot which talks about Lara's origin, Lara Croft, the protagonist. And well, this talk is about Shadow of the Tomb Raider. Shadow of the Tomb Raider is developed by Eidos Montreal. It's built upon the foundation engine, which is made by Crystal Dynamics. And Nixus, the place where I work, is responsible for the PC version, and together with NVIDIA, we chose to do some really cool ray tracing stuff, which is accelerated by their new RTX GPUs. Okay, but why did we choose ray trace shadows? So why not GI? Why not any of the other cool stuff that's possible? Why not caustics? Well, let's first take a look at how the game looks right now. So this is a scene in-game. I think the location is called San Juan Mission. Well, as you can see, the shadows look okay. It works well. It looks believable. But if you look closely, you can definitely see some things that are not quite right. So, for example, you can see some detachment in the red circle. And the detachment is because we always use a small Z bias in our shadow map rendering, and this is done so we avoid self-shadowing artifacts. And but yeah, the Z bias itself may cause some other artifacts such as detachment. What you can also see is that the shadow mesh, or the shadow doesn't really look like the object that is actually rendered. So you can see the crate. The crate has a mesh, and in real life, the mesh would just be open, and the shadow that's being cast by that object would be, you would see the mesh on the ground as well as in the shadow. But in this case, we use a separate shadow mesh because we run into some resolution issues. So the mesh would not look correct if we would simply use the same mesh as if we would use the same mesh in shadow map rendering as in normal rendering. So let's zoom out for a bit again, and let's first look at our results. So I usually like to show the final result first, so you can see what we've done, and then explain how we've done it. So if you can see, the shadows look much better. It's nice and crisp where it's close by, and it's a bit more blurry if the occluders are far away. And you can see the mesh, the detachment is gone, so that's all very good. And if you look closely, if you look, for example, at Lara Croft's bow, it has a nice shadow, but if we go back to shadow map rendering, you can see that it's kind of missing, and that's due to the same resolution issues we get with the mesh in the crate. Okay, so why did we choose to build ray traced shadows? Well, shadow mapping is not perfect. Everybody knows shadow mapping is not perfect. but we fake a lot and it works well. But still, there's a lot that shadow mapping cannot do, such as the pixel perfect shadows. We get some kind of we get a bit of resolution issues, such as with the mesh in the crate. It can do translucent shadows, so yeah, we'll talk about translucent shadows in a minute. It can do point light shadows, and we kind of fake it currently. So if we want to do a point light shadow, we fake it by using 2 spotlights, and we can do area lights, and we'll talk about area lights in a minute as well. Okay, well, let's talk about the XR shaders, and I'd like to ask Holger to come up on stage.
Okay. So I got my own mini agenda here. I'll talk about noise and random number generation. I'll tell you also why I actually talk about this. We'll talk about ray generation and the ray generation shaders. We'll quickly show you the hit shaders that we use. They're very simple, actually. We'll talk about adaptive ray tracing. That's a special feature we've used for the DXR ultra quality mode. And I'll also talk about translucency. That's also another feature that we only enable for the DXR quality ultra mode shadows. Finally, I'd like to talk about TAA and the post-projective jittering that comes along with that. And that, interestingly enough, created some issues for us with our shadows, and I'll explain why this is the case. Okay, I've also decided to give you a mini intro into DXR. So the idea is basically that DXR allows you to build acceleration structures that basically allow you to define a scene. And the scene, at the top level of the scene description is the TLAS, the top level acceleration structure. And in each top level acceleration structures have a couple of BLASs, or bottom level acceleration structures. And these finally contain the triangles, the real geometry. And what DXR allows you to do is write a ray gen shader, so sort of a compute shader that allows you to cast rays into this TLAS. And then for every hit it sees, it calls back into the any hit shader. Now the any hit shader can either preempt the ray there. It could basically say, accept this hit, then the runtime takes care of that. And then the closest of the accepted hits will then be finally passed to the closed hit shader, where you can, evaluate the results and do stuff with it. Okay, that was my really quick DXR intro. Okay, noise and random number generation. So why do we need that? So the thing is, if you have this very simple scene and you have this green blocker here and you have the sun, so ideally, if for any point in the scene to find out how much it can see of the sun, you want to cast many rays. So for this guy, let's say we want to cast many, many rays to find out it can't see the light at all, so it's in full shadow, it's in umbra. This pixel here can see at least a portion of the light, so it's penumbra, and this pixel can see all of the light. But in the end, you need to have many, many rays to find out, how much of the light you can see. So for great performance, we actually only want to shoot 1 ray per pixel. So how can we possibly do this? So the idea is basically, instead of shooting many, many rays, we use a neighborhood of rays, and each pixel in the neighborhood only samples or shoots 1 ray, but it shoots a ray at a random position on the light source. So let's look at this neighborhood. It's quite a small one, but this will do to demonstrate the idea. We transform these pixels to world space, and then basically this is our light source. This is a cone light in this case. And we then just basically make each pixel shoot a ray at a random position. So in this neighborhood, we sort of sample the same info we would otherwise sample in 1 pixel. Okay, so and then basically to generate these random numbers, we use, or these random positions, we use a pseudo-random number generator. And this is a link to the one we've used. And now the question really is, as with all these number random generators, is what seed do you use to seed the random number sequence? What we do actually is we use the seed that's derived from the 2D position of the pixel. And what works fairly well for us is just, we say C, that's basically the pixel 2D position, modular a certain tile size. So we're doing basically generating the same number generators after a certain tile, a repeated tile block of pixels. And yeah, that works fairly well for us. And this is a screenshot. Don't know how well you can see that. I will give you a zoomed in shot, but this is basically the non-denoised visibility signal we get out of casting these rays. It's a bit of a zoom in. You can see there is a sort of repetitive grid pattern, but the thing is, obviously, as you move your camera, then also the 2D position changes, so it's not stable with movement. Okay, so how do we generate rays? I mean, I've sort of explained this already, but we found that basically for each of the type of light sources we support, we support directional light source with an angular extent, so that's what's used for the sunlight. We support area cone lights, so where the light source has an area. We support point lights, where the point light is not a point but a sphere in reality. And we use rectangular area cone lights. It's a cone light where basically the light emitting area is a rectangle. Okay, and we found out that basically initially we had like one big radiant shader that supports all of them, but we found that specializing the shaders for each light type makes them run faster, so we'd gone for that. Okay, so when we shoot rays, what we do for all of the light types is that we look at the pixel normal, and we step a little distance along the pixel normal and start our rays there. This is just to prevent self-shadowing from happening. We don't shoot any rays for pixels that face away from the light. That makes sense and saves ray casting times. And this is what we do for the directional lights. We just basically generate random directions that are within this angular extent of the sun that I depict here with a yellow ellipsoid. Then for spotlights, it looks like this. For spotlights, we actually only shoot rays for pixels that are within A, the cone, and B, within the reach of the light. So depicted by this arc here. For point lights, again, it's very simple. Shoot only rays for pixels that are within the sphere of influence of the light. For rectangular lights, it's a cone light, as said, so if it needs to be within the cone, within the reach, and then we're shooting rays that sample enough of the rectangular area to understand how much of the light you can see. Okay, so let's talk about the hit shaders quickly. This is the only thing or the only slides where I show you source code. It's very, very short, so I think it would be okay to look at this together. All right, so, oh no, hang on. First of all, I want to tell you a bit of what we do in the hit shader. So the interesting thing is we don't use the closest hit along the ray from the pixel to the light. We actually accept the first opaque or the first hit we get. And by first opaque hit, I mean if we hit an alpha tested primitive, we of course need to do the alpha lookup, a texture lookup, and see if it is actually, if this pixel classifies as opaque or not. The only exception is actually for translucency, and we'll talk about this a bit later on. So yeah, as said, if we hit an alpha tested primitive, we need to basically, we need to get the fetch and texture coordinates for the primitive that is hit. This is the primitive ID you can get from the XR runtime in the shader. And then you basically fetch the texture coordinates, look up in the texture array and find out if this pixel is actually blocking the light or not. Okay, here are now the shaders finally. So let's look at the any hit shader for opaque geometry. So we have basically, in terms of shader binding tables, we only have two entries, one for opaque geometry and one for alpha tested geometry. And for the opaque geometry, the any hit shader just accepts the first hit it gets and ends the ray, and the corresponding closest hit shader just basically feeds back or returns the hit t, which is basically the distance along the ray along the shadow ray towards the blocking geometry, and it basically sets the visibility to 0. For alpha test geometry, it's a bit more complicated, but also very simple here. As said, if we fetch the alpha value, if it is below the threshold, we just ignore the hit, so with this, the array carries on. If it is above the threshold, we say, okay, we're setting visibility to 0 and accepting it, ending the hit, and then in the alpha close hit, we basically just store the current, or we just return the current hit T. We don't actually change visibility in the alpha hit closest hit shader because we run the same shader with the translucent shadow code that I'll explain a bit later on. And you'll see why this is why we don't touch the visibility as such. All right, let's now talk about adaptive ray tracing. Adaptive ray tracing basically is only used when you turn on DXR ultra quality shadows. And in this mode, we actually cast more than one ray per pixel for some pixels. So let's look at the details. So it's done in two phases, or even in two dispatch ray calls. The first call will basically cast 1 ray per pixel, and it would give you the results we've seen before. And then we cast up to two more rays when we think it's necessary. And how do we do this? So if you look at, these are the results from the hit shaders, right? You have the visibility value, which is initially just binary. So black means I can't see the light, white means I can see the light. And you have got some hit T value where darker means it's a hit that's closer to the origin, and white means probably infinity. It can see very fast. The block is far away. All right, so for a configuration like this, where every pixel in the neighborhood can see the light, there's no point in shooting any more rays. Same thing, if all guys are in shadow, yeah, why should we shoot another ray? But if we see configurations like this, and we actually look at hit T and look at the sort of do a variance analysis on hit T, if we see a sort of a mediocre or small variance, then we say, okay, let's shoot one more ray, and then we update the visibility to visibility 0 from the first phase plus visibility 2 from this cast, and divided by 2. So it's a non-binary visibility after that step. And similarly, if we get a really complex or more complex hit T situation, we shoot 2 more rays. And in this case, we also update visibility like this, and we basically sum up all the 3 visibilities and divide it by 3. So again, we have a non-binary visibility result here. Okay, and that obviously improves like the shadows and the visibility values where you have like more complex edges and so on. Okay, let's talk about translucency. So this is also a feature that we enable for DXR ultra quality shadows, and we support up to 3 layers of translucency, which means basically if the light goes, let's say, there's like just 1 layer of leaves above the ground, you'll have a lighter shadow. And if there's more layers, the shadow gets gradually darker. And we support 3 layers, mainly to keep performance at an acceptable level. And you would think that translucency should be straightforward with DXR. And I guess in the end it can, if you like, let's say, use the closest hit shader and then kick off another ray and so on until you've hit 3 rays. But this is 3 layers, but this is not how we do it. We want to basically use the any hit shader the way we use it in the non-translucent case. So the problem now is with DXR that the hits you get reported in the any hit shader don't come in a specific sequence, right? They can come in any order. So you might see this order where basically closest hit, conceptually closest hit is reported last. But you might also see that order. So this is the idea, right? So we thought about what can we do to make this stuff deterministic. And we've gone for a really simple solution. We just use subtraction, right? So for each layer we hit, we subtract 1/3 of the light. So if a pixel or if a ray hits 3 translucent layers, we're in full shadow again. Okay, so, and the modified any hit shader now is this. It again looks at the alpha value. If it is above the threshold, we subtract 1/3 of the light. And if visibility is low enough, we end the hit and set visibility to 0, but it's entirely possible that visibility may stay at some different value. And this is why we didn't change the visibility in the closest hit shader for alpha tested stuff. Okay, so this is a ray trace shadow with high quality shadows, which looks great. But this is one where you enable the 3 layers of translucency, and you can clearly see, right, where the ray just hits like 1 or 2 layers and where all the light gets blocked. Right, so let's talk quickly about TAA and jittering. Like many games, Shadow of the Tomb Raider uses jitter TAA, which means each frame adds a random subpixel offset to all geometry that is being rendered. And this surprisingly creates problems with flickering shadows, or has created problems with flickering shadows for us. And I'm going to explain why. So basically, the thing is, if you look at this 2x2 pixel grid, and here the red dots are the pixel centers, and this is where actually stuff that's being passed to the pixelator that is going to be interpolated across some primitive is going to be sampled. So if you then basically try to, in this case, rasterize a 3D quadrangle, in this case, the positions in the grid have nothing to do with rasterization. They're just there to give you an idea of how the 3D positions change across the quad. But you can see here, right, that if you look at the topmost, top left red dot, that basically the position that would be sampled there would be like something like 003. If you now jitter this thing a bit, you see that it would sample a totally different position, right? So somewhere between 003 and 103. Right, so basically jittering means that jittering changes the world space positions a pixel sees. And this also means it changes the depth value you see. And as we reconstruct depth from this jitter depth, the world space position from this jitter depth value, we got jittering world space positions, and we got jittering ray origins, right? And this, this interestingly enough creates problems in some places, not everywhere, but specifically where you can see, have a flat, let's say a flat ground, you can see reasonably far, and then you have big world space difference between like adjacent scan lines. And this means the rays jump around quite a bit. And if you then shoot just one ray per pixel at some, let's say, fine geometry, then you could get flickering in the shadows. And this also actually happens with shadow map filtering in Shadow of the Tomb Raider. It's just not as visible. You can see the shadows jittering as well a bit, but it's because shadow mapping does sort of image space filtering a lot more, or does a lot more taps than just one ray per pixel. You just don't realize it. So I've tried to capture this in the video, and I hope it's zoomed in enough so you can see. So I want you to look at the pixels in the ellipse, and I hope you can see some flickering. Yeah, I guess you can. I hope it's visible. Right, so this sort of flickering is what we got, and that's obviously not acceptable. So we thought what to do about this. And the current solution that is in the current patch out there is that we actually render an extra depth prepass that renders non-jitter depth. And we use this non-jitter depth buffer to reconstruct world space positions, and this fixes the flickering issue. For the future, we thought about rendering DDX of 1 over Z buffer Z, because that's linear in screen space, and then we could use this information to reconstruct a non-jitter depth value. Right, okay, this concludes my part. So John will take over from here.
Hi everyone. So I'm going to give you guys a very brief overview of the GameWorks spatial denoiser. So this was written by Edward Liu and myself, and it's what's used to denoise all of the shadows in Shadow of the Tomb Raider. So first up, I want to go over the inputs and outputs that are used by the denoiser. Holger mentioned visibility and hit T extensively in his section of the talk, and so those two buffers are rendered at full resolution and are obviously inputs to the denoiser. The other things that you'll have probably knocking around in your engine are a set of normals, world space normals, and also your primary depth buffer. And on top of that, because we're doing this per light, we need to input some light descriptor parameters. So this would be, is it a rectangular area light? Is it a directional light? If it's a directional light, then what's the cone angle? And so on and so forth. And then the denoiser just magically belts out a beautifully smoothed out image. And by the way, these shots are not taken from Shadow of the Tomb Raider. They're taken from a sample application which ships with the denoiser. But this is, that smoothed out image is just 1 ray per pixel and then denoised spatially. So there's no temporal component here, so you're not going to get any latency or odd artifacts as you have fast-moving objects and so on and so forth. So one of the key things that we noticed when we started to look at spatial denoising for shadows was that if you just use an isotrophic kernel, so just a circular kernel in this case, what you tend to see is that as you start to use slightly more complicated light sources, so for example ones which are say point lights, and then you start to drag them down towards near a plane, and then you put these thin poles close to it, you can wind up with situations where the denoiser is producing an okay result, but actually if you start to compare it to a ground truth image, it doesn't match up too well. And so one of the things that we did was we switched to using an anisotrophic kernel. And this is done effectively by projecting the light source down onto the receiving plane and figuring out what the major direction axis is, and literally doing your sampling in screen space along those axes rather than just straightforward X and Y or horizontal and vertical. And this yields a far more realistic shadow where you don't get this horrible overblurring occurring. So that's one of the major things that the spatial denoiser does to improve things. The other problem, this old chestnut, is overlapping penumbra. So if anyone's played around with PCSS or CHS, they will realize that when you have overlapping penumbra, so you can imagine Lara walking under a tree, you get some interference of the faraway blockers or occluders and the close-by ones. And it's quite hard to resolve within the filter kernel what the correct result should be. So you get this interference occurring. And here we can see in the foot of this dude, his foot shadow is getting interfered with by a shadow from a window frame which is off screen but is casting a much more blurry shadow. And you can see that the definition of the foot shadow is just starting to disappear as it enters into the penumbra of the other shadow. And that typically is quite a difficult problem to solve, especially if you're doing just spatial screen space denoising. How do you try and untangle that? So the spatial denoiser that we've written does largely fix that problem, and effectively what you do is you look at the hit T value at the center of the kernel, and you estimate how hit T should change across the kernel, and then as you step across the kernel, you inspect the sampled hit T and just take a simple ratio between the estimated hit T and sampled hit T, and it gives you a weight value which you can multiply by. And it basically filters out hit T values which you don't really want to include in the kernel. And it does a pretty good job of it, and it's quite cheap. So we found it to be extremely effective. And you get your foot back. So bleeding artifacts. So this is certainly a problem that you run into when you're doing any kind of separable filtering. And if you want to start filtering at half resolution and then upscaling, then it becomes an even bigger problem. And so in order to solve this kind of thing, where you can see coming off of the chest and the hand of this character, you can see there's these kind of like lines of artifacts which have sort of bled across from the character into the background. And we obviously want to try and avoid that kind of thing from happening. The image on the right is the fixed version where we've basically effectively detected the depth boundaries and made sure that bleeding doesn't occur. So what the spatial denoiser does is it has a customized depth boundary detection, and basically it only detects boundaries which it feels are going to cause problems for the denoiser. So it tries to keep those to a minimum. And these are written to a mask so that we can ensure that we separate simple pixels from complex pixels and treat them differently. And that allows us to avoid these unsightly bleeding artifacts. Last up, one of the things we noticed was in many scenes that you can do a lot less work. And specifically, if you look at that scene there, it's very clear that the only pixels that really need denoising are the penumbra pixels. Everything else is just black or white. So we wrote a bit of software which would detect where the penumbra pixels are and mask those out to ensure that we do the minimal amount work possible. And there you can see there's the penumbra mask. Now obviously that won't help you in scenes where the entire screen is penumbra, but I guess it depends on your game content, your style of game, and where your camera typically tends to go. But certainly in Shadow of the Tomb Raider, most of the time it has a really big impact on performance. Some other features, so half-resolution denoising, I briefly mentioned. This is actually used throughout Shadow of the Tomb Raider, so it's been deemed good enough quality for both the sun and for all the other light types. It does drastically improve performance over the full-res denoiser, something like 2 to 3 times faster. And because of the fact that we're using depth boundary detection, all of the complex pixels are actually denoised at full resolution, and the simple pixels are done at half resolution, so you tend not to notice, you don't lose edge quality from it. The other thing that we support is MSAA input of depth and normal buffers, but you can still ray trace at single sample resolution, which obviously makes things quite efficient. And what the denoiser does is produces an MSAA shadow mask, which is respecting the MSAA depth boundaries. And the last thing to mention is viewports. So if you imagine like a candle sitting on a table, it's only casting shadows in a very small area around itself. So obviously what you want to do is make sure that the denoiser and the ray tracer are not actually being executed for pixels that they don't need to be for that light source. So this denoiser supports supplying sub-viewports and ensuring that the denoising work is confined to that area of the screen. And I think we were able to support up to 12 lights, 16 lights. Obviously, if they're all overlapping, you're going to take a performance hit, but if they're spread around the scene, then you can handle quite a few lights like this. Okay, I think that concludes my section. Yep.
Okay, well. Yes, okay. We now have our ray gen shaders and we have our denoiser, but we still need a world to cast our rays in. So let's talk a bit about the acceleration structure. So Holger already mentioned BLAS and the TLAS. So the BLAS is, well, you can basically compare it to a mesh. It's like it's like a representation of one of your objects, one of your of geometry. So what DXR needs is DXR needs vertex and index buffers for all your geometry. So if you want to construct a BLAS, so you need the corresponding vertex and index buffer. And for static geometry, such as a table or a chair, it's straightforward. You can just supply your existing vertex and index buffers and call the create expression structure function, and it will magically create a BLAS. However, for dynamic objects, this is not as straightforward because we need to fully transform our vertex buffers before supplying it to the create acceleration structure function. So, and to make matters worse, the foundation engine actually uses shader graphs, which means that each object can have a unique vertex shader. It's not entirely true, of course, and not every object will have a unique vertex shader, but in theory it's possible. So what we did to fix this problem is we added the shader permutation to our shader graph builder in our vertex shader template, so that if you enable a flag, it will output your vertex buffer into a separate new buffer, and it's fully transformed. It's just using the shader graph, the same as with rendering, only exporting it to a buffer. And if we do this in a pass just before creating the acceleration structures, then we have all the information we need. Well, as long as you're interpreting your bones correctly. Otherwise, you get like inner demons. Anyways, moving on. One exception was Laura's hair. Laura's hair is actually generated. It's generated using pure hair, which is an evolution of AMD's TraceFX. And what TraceFX does, or pure hair does, is it simulates control points. So it determines how the hair would look, and it creates control points in world space. And it renders it as camera-facing quads. But if you want to build an acceleration structure, we need to have actual geometry. So what we chose to do is just do the simplest thing possible. So we created like one cylinder for each strand, and we chose to do the simplest cylinder possible because we're just doing shadows, and this seemed to work well. And yeah, the simplest cylinder possible looks a bit like a famous chocolate bar. Okay. The thing is, if you have dynamic objects, then it will probably change every frame. If you would just say, okay, my skinned object, like a character, has changed, we could say, okay, we're going to build a new acceleration structure and throw away the old one, because the old one is not valid anymore. But that's not very efficient, as you can imagine. But luckily, in DXR, there's an option called refitting. And refitting means that you're actually updating an object. So if you have like small model changes, so if a character is animating a bit, or you have like a tree that's waving in the wind, that constitutes as a small model change, and then you can use the refit model. And the reason why you can only do it with small model changes is that if the changes are big, then your ray tracing performance might degrade. But in our case, that didn't seem to be a problem. For us, we could just refit all our acceleration structures every frame, and we didn't see any performance degradation. So that was good. There was only one exception. We can only refit if the number of vertices are the same. So if the number of vertices change, then we need to rebuild it. And for example, Laura's hair has an LOD model which adds or removes strands, and yeah, we needed to rebuild it in some cases. Okay, so now we have all our objects. Now we need to build a scene. We need to build a TLAS. The cool thing about TLASs, yeah, you can say it's a scene. The cool thing about them is that you can instance BLASs. So you can use the same object multiple times, but this obviously only works for static objects, because if you have a dynamic object, then well, the pose will probably be different, and it's hard to match them. For TLAS, you can also do the same as with BLASs. You can rebuild or refit them, but in our case, we didn't see any reason to refit it. Rebuilding seems to be fast enough, and even the NVIDIA driver team recommended just always do a rebuild. Okay, so what kind of objects should we put in the TLAS? So suppose you have you're rendering a scene. You're probably going to use some LOD. So in front you will have like a super high density mesh, and in the back you use something simple, maybe an imposter mesh. It could be anything. For us, every lot level will be stored in a separate BLAS. So we can, if you want to instance them, we can instance different LOD levels. But when we started this, we thought, okay, we want the best shadows possible. So we want the highest density models. We want to use the highest density models. So we just use the highest lot level for everything. However, as you can read, this caused some self-shadowing artifacts. So in the end, we just use the same LOD we use for rendering. There's one caveat, namely if you are blending between LOD levels. In our case, we have a datum pattern. then you can, how do you do this in the acceleration structure? So in our case, we just chose to insert the LED with the highest opacity value. So there will always be only one LED for every object in the acceleration structure. Okay. Now we have our radian shaders, we have the denoiser, we have our world, our acceleration structure. So how do we integrate this in our render pipeline? So let's look at a very simple representation of our render pipeline. It's missing a lot of passes, but I just want to focus on these couple of passes. We use a Forward Plus render in Shadow of the Tomb Raider, so all the shading, all the lighting, all the shadowing will happen in the forward opaque pass. So what do we need to do to add ray traced shadows to this? One thing I forgot to mention, the shadow resolve pass is actually a pass that resolves our shadow maps in a texture array, and each slice in the texture array corresponds to a screen space shadow mask. This is important for ray tracing. So if we want to add ray tracing, we need to add a couple of passes. So we need to add the vertex transform for our dynamic objects. We need to build the acceleration structure. As Holger mentioned, we need a non-jitter depth pass as well, so we added that as well. And we can replace the shadow resolve by our ray trace. So by our ray change shaders and then the denoise. And then we get a shadow mask. Okay, and this is good news because we now don't need to change anything in our forward opaque pass. So that's good. We don't need to have any shader changes. It just works. Okay, let's look at some timings. So this is all very, very coarse. The timings are not well, they're not real world, but let's just assume that they are. So if we want to optimize this, how do we do that? Let's look at some dependencies. So as you can see, the forward opaque pass is dependent on the shadow resolve pass, and the shadow resolve pass is depending on the shadow map pass, the depth pass, and the acceleration structure pass. And the acceleration structure pass is depending on the vertex transform pass. So if there are any console developers in the audience, they will probably scream, async compute. Well, yeah, that's what we thought as well, async compute. So it turns out that we can do the acceleration structure building in async compute because it's actually a compute step. So that's, and since there are no dependencies to the shadow map pass and the depth pass, we can run it async with these two passes. And we hide 4 milliseconds. That's good. If you're paying attention, then you probably will say, hey, what's that pass doing there? Why is there still a shadow map pass? I mean, we were gonna replace our shadow map rendering with ray trace shadows. What's going on? Okay. Turns out we still need to have shadow map rendering. And why do we still need shadow mapping? Well, one of the problems is that we also have translucence. And if we want to render translucence, then we cannot use our shadow resolve pass. And why can't we use our shadow resolve pass? And we can't use our ray tracing because we don't have world space positions for those translucence. And we could do something like maybe depth peeling, or if we could maybe shoot our rays from pixel shaders, then we could maybe figure something out. But currently that's not the case. So in this case, we kind of decided for our translucence, we still use shadow mapping. Another reason why we still use shadow mapping is performance. So suppose we replace all our shadow mapping with ray tracing. Then that means that our acceleration structure will basically contain the entire world, because almost everything is LED. The problem that we encountered was that updating our entire scene full of dynamic objects was super expensive. It just blew our budget. And it was mainly in the, Shadow of the Tomb Raider has a couple of jungle scenes where there's a lot of foliage, and all the foliage were done using simple vertex animations, and well, there were just a lot of objects, and it turns out it wasn't really feasible to update them all in one frame. So what we decided to do was to call our acceleration structure. So what we're doing is we're using the existing shadow map calling to call objects out of our acceleration structure. Oh, what does this mean in practice? So for directional lights, what we did was, if you have a directional light, then basically you still have the entire world in your shadow frosting. It's not entirely true, but it can be that most of the objects are still in your frosting. So what we decided to do was to only replace the first couple of cascades with ray trace shadows. So we only replace the first two cascades with ray trace shadows, and the rest is still shadow mapped. And that's visually you don't really notice it, but performance-wise you do notice it. And for local lights, so for example for spotlights, for point lights, what we do is we add a maximum distance. So at a certain distance, at a certain distance, the ray trace shadows will just fade away, and the rendered shadow map will be visible, and at one point the ray trace shadows will be completely off. But how do you choose these distances? I mean, we're programmers, we're smart, but if you want to make something pretty, you do need artists. And so what we decided to do was to give our lighting artist just a whole bunch of buttons and knobs to turn, and just give them all the things to tweak, so that they can get the best visual effect and with the best performance. Okay, so now we have all the building blocks. So let's look at some of the results. These are just a couple of screenshots, and they kind of speak for themselves. But these are 2 point lights. And as you can see, currently there's no shadow. And if we turn it on, then there's some nice shadowing going on. And this is, it's kind of outside the screen, but there's a billboard just above the screen, and we authored it as an area light. But yeah, in shadow mapping that doesn't mean anything, but with ray tracing it does, so you have really soft shadows. See? And another example. This is just a directional light with a lot of foliage, with a lot of elf testing. And you can clearly see that the character is really crisp and a hard shadow, and the foliage is a bit softer because it's a bit further away, and there's some elf testing going on. So that's really nice. Okay, well, we've got all the tech now. We've authored the entire game. We've actually released the patch. What's left to be done? There's still work to be done. So these are just some examples of what we could do to improve it even further. So as Holger mentioned, we can, instead of adding the non-jittered depth paths, we can reconstruct the non-jittered depth. We can think of ways to do ray trace shadows on translucent geometry. We haven't touched tessellation at all, so tessellation is kind of, we just use the non-tessellated meshes. There are ways to improve ray tracing even further by authoring the content even further. What we could do is we now have a vertex transform pass that actually runs your vertex shaders and outputs a new vertex buffer. And we could actually use that buffer in the rest of the passes as well. It might save some performance. We haven't tested it, but I can imagine that it could be a nice optimize. And obviously, we don't need to confine ourselves to shadows only. We can do all kinds of other neat stuff with ray tracing. Okay, that concludes our presentation. So if there are any questions, I don't know if there's time, but I think there is. So if there's questions, you can please come to the microphone and we'll try to answer them.
I've got a question regarding the denoiser. So you talked about doing some simple and more complex, or denoising of simple and complex pixels. How is that handled? Is it just a control flow in a shader, or do you do some compaction and separate them into separate passes?
To be honest, I don't really know because I haven't written the denoiser, but I believe it's in this case really control flow. Yeah. For some of the stuff like the penumbra mask, we actually use the Z-buffer, so we do use the Z-buffer to color work. But I believe for this stuff, it's really control flow in the pixel shader. Yes.
Okay, thanks.
Thanks a lot for the talk. I have a question regarding the culling of the directional shadows for the acceleration structure. Do you do some kind of pre-computation, for example, for sunlight shading? Because you could kind of know beforehand which geometry is in the interior and will never be visible for sun shadows, something like that.
Well, what we did was we just used existing shadow map culling. So, in the case of foundation, there's actually some portal culling going on. So if you have like an exterior scene and a separate interior scene, there's probably there's a cell around the interior scene and there's a portal, for example, in front of the door and in the windows. So the culling is done using that.
Okay, great, thanks.
I know you mentioned having keeping the shadow buffers around for lights, but otherwise, was there any difference between how you were able to approach static versus dynamic lights, and maybe how many dynamic lights you could have, or that sort of thing?
No, there's no difference in static and dynamic lights. We just render our shadow maps, and in this case, our ray trace shadows every frame. We could do maybe do something special for static lights and static geometry. To just maybe cache them and only render the dynamic object in there, but that's not there. So there's no difference in static and dynamic lights.